Hello, everyone. This is Smart Cross Team 17. My name is Brandon McDonough,
I'm
Josue
Morgado.
I'm Ken Maguire.
Vishal Kumar.
and our advisor is Dr. Zunoubi, and our sponsor is from the New York State Department of Transportation. This is our presentation board. We'll be going into different components of our project and each explaining what we contributed. From the beginning part of the flow chart here, we have a MAC address, which is the media access control from someone's phone, and it's turned into a signal through a signal processing in an application.
The step in the flowchart is a force applied by a pedestrian walking over the sidewalk, which would trigger the piezoelectric plates underneath the sidewalk, which would send an AC voltage to the AC DC signal processing, and then it will send it to the PCB board.
And at the end of our flowchart, we have the PCB, which takes input from both the Bluetooth and Wi-Fi signal processing and the piezoelectric system, and uses these two inputs to control the traffic control system and react accordingly.
The piezoelectric portion of the project is designed to detect pedestrians nearing an intersection. The pictures shown below are the final design of the piezoelectric system. The top right picture is the piezoelectric plate. The two left pictures are the casing for the piezo benders, and the bottom right is the piezo bender, which the piezo material would lie on top of. The point of the piezo bender is to keep the piezo plate from bending more than 1 millimeter. Anything above 1 millimeter deflection would damage the piezo plate. Seen in these pictures, the left picture is the complete final design with every part put together. The casing would be made out of a carbon fiber. The piezo benders would be made out of 1010 hot rolled steel, and the lid would be made out of rubber. The right picture is a close up of the design too.
So for this project to function properly, there needed to be a solid power distribution layout in place. This layout was responsible for taking a 48-volt AC signal from the piezoelectric system and converting it into a 5-volt DC signal to be used for the traffic control system. Here we have an initial breadboard setup of the layout, which includes a bridge rectifier for AC to DC conversion, a voltage regulator for voltage step down, and a resistor capacitor filter. Here we have the updated power schematic. To make the signal more smooth, we decided to add a power transformer and a voltage regulator and an extra capacitor to smoothen the signal out more before it reaches a 5-volt output.
Next, we have the Bluetooth system and application. On the left, you can see the home screen of the application. On the right, we have our electrical cabinet, monitor, monitor adapter, and Raspberry Pi. I use the Raspberry Pi to house the application and able to use it as a Linux system. The adapter in the top right fixed the issue of displaying the monitor from last semester. In this next slide, I displayed some of the code from the application. It takes the array of MAC addresses from all the phones around the sensor and uses it to manipulate a digital signal to be sent to the traffic controller to change traffic lights. You can see that in the application, you can adjust the parameters of the intersection, such as the latitude, longitude, and signal ID, and then it will be incorporated with the code at the end.
So tying it all together, we have the traffic control system that will be written to a PCB. On the left is the prototype at the end of Senior Design 1, which is written to a breadboard. It was decided that we did not need the pedestrian countdown timers as they were not vital to a proof of concept on this project. It could be seen that one microcontroller is driving the traffic lights while taking input from both the piezoelectric system and the Raspberry Pi MAC address detection system, and is providing input to a second microcontroller that is driving the LCD diagnostic portion of our project. In creation of PCB, all circuitry must first be written to schematic so that it can be imported to a layout. This is the root schematic of SmartCross. Microcontroller 1 will take input from the Raspberry Pi and piezoelectric system. There will be shared output from the microcontroller between the traffic lights and the diagnostics. And finally, the second microcontroller outputs to an LCD, which provides remote output of how the traffic intersection is reacting. There's also a power supply and boot block in the bottom left, which will have any reverse voltage protection or regulation, indication LEDs, things like this. All these schematics can be seen in the engineering notebooks. Finally, we have the finished PCB. We could see from the left is the layout before it was manufactured on the right. It could be seen that all the outputs were kept in either terminal blocks or a 12-pin header. The inputs from the piezoelectric and Raspberry Pi are on Molex connectors. Power planes were used for maximum dissipation, and the microcontrollers have a minimum trace for maximum data transfer.
When applying this application to modern traffic systems, we hope that this will accomplish our goal of higher safety to pedestrians across the state.
Going forward with this project, we believe the next step would be to actually get everything printed out and assembled together and testing it out real world applications such as an actual intersect.
This was Team 17. This is our project called Smart Cross. Thank you for watching. I'd also like to thank Dr. Zunoubi and the New York Department of Transportation for helping us out with this project. Thank you.